now. Okay. Thanks for inviting me to give a tutorial talk here. And the talk is about long-tailed visual recognition or long-tailed classification. And this talk will cover most of the works from Kang Bingyi, and Bingyi also prepared the slides. But due to the presentation time limitation, we can only one person to do the representation. So I will give the presentation. As mentioned by Yizhe in his wonderful talk, the classification is actually the bottleneck in realistic problems. Here, our topic is about long-tailed classification. That is a very realistic but also challenging classification setting. So I will first give a brief introduction or definition for the long-tailed classification problem. Then I will resolve this problem from two aspects. One is how we can do the classification better, and the other one is how we can do the representation learning better for long-tailed classification. And finally, I will conclude this talk. Okay, so long-tail is actually a very common phenomenon in realistic data or other neural facts. It is actually depicting such distribution, that is the data from different classes for classification problem. The data for different classes, the number is not balanced. They are not uniformly distributed. Some classes may have many training instances that is dominating the overall data set, while some others may have very small number of training instances. So if we take an overall look at the number of training samples per class we can collect for training the classification model, then the distribution is actually presenting a long tail shape. And we can divide these classes according to the number of instances they have into the many short categories, medium short categories, and the few short categories. Or we can also call them head classes or tail classes. This is a very common problem or very common phenomenon in the realistic data distribution. But unfortunately, in our laboratory setting, we usually artificially balance the training set in terms of their training instances, such as for the internet of MS COCO, the number of instances per class is actually artificially balanced, but this is actually not true in the realistic data distribution. A more closer to the realistic distribution setting is this long tail setting. That is, the number of training instances per class is not actually uniform. They are following a long tail distribution, but the testing data may come from or may form a balanced or uniform distribution. So the challenging is actually the distribution is mismatched between the training distribution and the testing distribution. We know that the basic assumption about statistical machine learning or deep learning is that the training distribution is actually presenting the similar characteristics as the testing distribution. Otherwise, we may fail and we will face the generalization issue. Long tail is actually featuring such distribution match. The training distribution, as I mentioned, that is a long tail distribution, while the testing distribution is a uniform distribution. So there are actually, this is a long-standing problems, both in research and in industrial applications. And there are also a bunch of different solution approaches developed from different aspects. We can roughly categorize them into three main streams. One is we can do the rebalancing. This is a very straightforward solution. We know that the long tail, the tail class does not have sufficient training instance. So we can upsample this class training instances by random or by data augmentation or by just repeating the data during the training process. This is the upsampling the tail classes, or on the other hand, we can downsampling the head classes to artificially balance the number of training instances. And but this cannot provide any new information because we do not have any new data coming in for training the model. So the performance improvement is not very significant, even though they may work well to some extent in realistic applications, but this does not essentially address the challenge from the long tail classification. Then the second solution is from the other aspect, that is to rebalance the training loss. We know for the long tail classification, we are training a classification model that is based on the surprise learning. So the model will be biased by the training loss definitions, by the training loss computation. For the head class or for the many short class, they will contribute more to the loss computation than the tail class. So the trained classification model will be biased to the head classes. They will perform better on the head classes, but perform poorly on the tail classes. So another solution is we can rebalance the loss. We to tailor the contribution of the head classes, the tail classes to the total loss computation to be balanced or to be equal to each other. A simple way is we can increase the weight for the loss computation from the tail classes, while decrease the weight from the losses computed on the head classes. So that are the rebalancing the loss solution. And the third one that is actually a quite promising one, but there is not a very good implementation so far. That is transfer learning. We know that even though the data they are from different classes, but they still share some knowledges that may be benefiting the recognition or classification for each other. But this knowledge is very implicit, maybe in attribute level, maybe in some abstract format. So that is very hard to formulate them how to do the mining or the utilization of the knowledge. But this is a belief that in the future we may see some work that can transfer the knowledge learned from the head classes to help the recognition for the tail classes. That is transfer learning based approaches. But in this talk, I will introduce another new standing point for solving the long tail classification problem. That is whether we need to always couple the representation and classification model learning together. We know that the key factor to the success of deep learning is the end-to-end learning. We learn the representation of the data under the classification model or classification model together with the representation. That is end-to-end training. But it is not always necessary to perform the best for different classification or recognition problems. At least the long tail classification is actually not the case. So let's see how we can how we get such a conclusion based on our empirical study that motivates us to decouple the representation and classification model learning. So here is a rough description about the factors affecting the final classification performance for the long-tailed problem. We know the deep learning model, they has two key parts. One is the representation learning, and the other one is classification model learning. They are together determine the final performance of the classification model. If we are doing the normal training, we do not provide any specific treatment to the data set or the training approaches. We are doing the normal training, then the representation quality may be very high because we are well utilizing all the data for the representation learning model learning. But the classification model may be not so good. The quality of the classifier may be heavily biased to the head classes, and the quality is not so high. So overall, the performance may be not so good. The other solution is we do the resampling on the tail classes. We enrich the tail classes by some pseudo resampling or pseudo data augmentation. Then the representation may be hurt because we are overly relying on the repeated sample to learn the representation. But the upside is we can improve the quality of the classification model. So maybe the total performance, the overall performance of the final classification model can be further increased compared with the normal training. But this is still not a very effective solution because we are at the cost of representation learning quality decrease in order to get a marginal increment on the overall performance. So ideal solution is if we see the classification model training by isolating these two components, then an ideal solution is we can keep the quality of the representation learning as the one learned from the normal training, but we can further increase the performance of the classification model. Then put them together, we can get an even better performance for the overall classification model. So this is our motivation for decoupling the representation and the classification model learning. Here is a side note that such observation is based on some rough empirical studies, and this is actually not a very rigorous argument. So this talk, as I mentioned, I will focus on two parts. One is the classification, decoupling the classification model learning and the representation, and focus on the classification learning in the first part. And in the second part, I will introduce another method for improving the quality of the representation learning, which is called KCL. KCL, as I will detail later, KCL can improve the data representation quality, and meanwhile also improve the quality of the classification model and gain a better model performance for the long tail classification. But let's see the first part. So we are aiming at a better classification model while maintaining the quality of the representation. So we should decouple the representation and the classification based on the intuition. And I will make this more clear based on the empirical observations. And we are going to illustrate how we can improve the classification performance while not hurting the representation quality. And the second part will be focusing on the how we can get an even better representation, such as this is based on the studies on what kind of representations are good for long tail recognition problem and how we can learn such good representation. So let's see how we can do the classification model to a better quality. We start our empirical studies with revisiting the sampling strategies. We know that the very straightforward solution to improve the long tail classification model is to do the resampling of the training instances. So there are two common sampling strategies. One is we do the instance balance sampling. That is, we just respect the original data distribution. We sample every instance with the same probability. So the result is the head class will be sampled more frequently during the training than the tail classes. And the other one is the class balance sampling. We manually rectify the sampling probabilities for every class to make sure that every class can be sampled with the same probability. So if these two sampling strategies can be unified into a single formulation as shown in the above here, the PG is the sampling probability for the class J. It has two factors contributed to its probability. That is the number of instances sampled from the JS class divided by the total number of instances sampled during the training. And we introduce another hyperparameter Q here. This is actually tuning. This Q can tune the sampling strategies. To see that if we set Q equal to 1, then these sampling strategies will be corresponding to the instance balance sampling. The sampling properties for class J is totally determined by the number of instances, proportion of the instance in the overall instance number. But if we set the Q equal to 0, then that is the sampling probability is not dependent on the number of instances per class. Every class is given the same sampling properties. Then we can also translate the Q value to an intermediate value between 0 and 1, such as we can set the Q equal to 1/2. This will give us another new sampling strategies. We call it square root sampling. Or we can dynamically tune the value of Q to interpolate from the instance balance sampling to the class balance sampling during the training procedure. This is called progressively balanced sampling strategies. This figure is plotting the result of the sampling properties from different sampling strategies. The left figure, the black curve is showing the sampling property for the classes following the instance balance sampling strategies. So of course, the head classes will be sampled more frequently than the tail classes, while the green curve is showing the class balance sampling method. Every class is given the same sampling properties. Then the square root sampling method is lying between these two methods. And we can progressively tuning or changing the sampling methods by tuning the value of Q. It will generate different sampling properties as shown in the red figure. So these are the sampling methods we will investigate in our following studies. Then let's do a first empirical observations about we are trying to understand what is problem with the classification model for the long-tailed classification. So we plot the weights for the linear classification model parameters for every class separately, and we plot their weights in this figure. So this figure is showing that the dataset distribution is as shown in the dashed line, that is a long-tail distribution. And the blue line, the blue curve is showing the weights or L2 norm of the classifier weight for every single class. So interestingly, we can observe there is a correlation between the number of training instance number, the training instance number per class, and the weight of the classifier. For the many short classes, the training instance number is large, and the weight classifier, the weight of the classifier is also large. Well, if the training instance number decreases, then the weight classifier is also decreasing. So this is a very interesting observed correlation between the number of training instances and the weight of the classifier. So based on this observation, we found that for the tail classes, the classifier also usually has a very small weight in terms of the L2 norm of its parameters. Also, it has a very poor performance on the tail classes. So this comes a hypothesis or natural hypothesis, that is, the classifier weight may determine or may contribute significantly to the performance on the classification accuracy for the corresponding classes. Then we can, from this viewpoint, we can try to improve the classifier by adjusting the classifier weights to see whether it can improve the classification performance for long-tail setting. So we try different approaches for adjusting the classifier while keep the representation frozen. We do not update the representation part of the dependent model. So the key is we need to break the norm of the classifier and the class size correlation, and we propose 3 ways to achieve this target. The first method is called classifier retraining, CRT for short. For this method, we freeze the representation, and then we retrain the linear classifier with a resampling method that is based on the class balance resampling to get a balanced classification model. And we can observe, as shown in the blue lines, the classifier weight is indeed rebalanced. This is working well for adjusting the classification model weights. Then the second way is tau normalization. That is, we do not need to do the retraining, but we can simply normalize the weight norm of the classification model. Here is the formulation, and we introduce a tau parameter, which is called the temperature, for adjusting the degree of the normalization. The result is shown in the yellow lines. And similar to the classifier retraining, it can also rebalance the norm of the classification models for all the classes. The few short category classifier magnitude can be boosted to be similar to the magnitude of the many short classifier. Then the last one is learnable scaling factors. That is, instead of manually setting the value of the tau, the temperature hyperparameters, we can make it learnable by learning the scaling factors end-to-end together with the classifier training. And the result is as shown in the red lines in the left figure. The effect is very similar to the tau normalization. Okay, so all the methods are quite simple, but it will be very interesting to observe the combination effect by combining the different sampling methods and the different classifier treatments, such as the retraining or the tau normalization. So we plot the performance, we evaluate and plot the performance of all the different combinations and show them in this figure. From the rightmost figure, we can see that on the rightmost figure is showing the overall accuracy for other classes. And we enumerate the different training methods, including the joint training. That is, we train the classification model jointly with the representation without any specific treatment. This is a very naive baseline. And also the other methods, including the we do the classifier retraining and the tau normalization, and we combine them with different sampling methods, including the instance balance sampling, the class balance, and also the square root rebalancing and the progressive rebalance. So we have a number of different combinations. Then we can observe the result in this plot, and we can make some observations. The first one is highlighted in this these boxes without any classifier rebalancing. Namely, we are using the naive joint training. Then the progressive balance sampling works best. But if we do the instance balance sampling use and we do the classifier rebalancing, then the medium short and the few short performance can be increased very significantly and achieve the best performance. That is much better than the joint training. So why the rebalancing over the classification model can work so well? Here is an intuitive explanation. Without any rebalancing, then the classifier weights of the tail classes will be dominated by the head classes. Then the classifier weight is actually proportional to the area of the decision area of the corresponding classification model. A classifier with a larger weight will span a larger area for the decision. So it will dominate in the feature space. While the tail classes has a smaller weight, the decision area will be smaller. So if we do the rebalancing to adjust the classification model weights, then the decision area will be similar to each other. So they are basically generalizing similarly to the test set. And we do the experiments to evaluate whether the decoupling we learn the representation at first and freeze the representation and do the classifier training. We see the results on the ImageNet LT and the initialist data set. Here is listing the result. From the result, we can see that the decoupling approaches, even though it is slightly sacrifice the accuracy on the many short classes, but it is indeed achieved the best performance, overall performance. It can improve the medium short and the few short classification performance very significantly compared with the joint training. On the initialist, we can make the same observations. And once the representation is sufficiently trained, we can achieve a better performance by training the representation, by training a better representation model and freeze this representation and retraining the classifier or readjusting the classifier. Okay, so we talk much about the classification model training. Then how about the representation? We know that the representation is actually usually the representation is learned in a supervised learning manner. But in recent 2 years, there is another very popular trend that is utilizing the self or unsupervised learning to learn the representation. And there is an interesting observation on the quality of the representation from the self-supervised training. That is, the self-supervised training will generalize better than the supervised training onto the downstream tasks, even though they are performed poorly than the supervised training on internet, but they can generalize better to downstream tasks. So this reminds us whether we can explore the self-supervised linear method to learn the representation, because it does not utilize any semantic label information and will get rid of the semantic classes, bias, or imbalance problem in the learning process. So we start with a pilot study to see how the supervised training based on the cross entropy and the self-supervised training based on the contrastive learning, how the representation quality is affected or sensitive to the balancedness of the data set. We manually created a different data set from by controlling the imbalanced degree. So the LT0 is the most balanced data set. Every class have the same training instance number, and the LT is the most imbalanced data set. It is the naturally long tail data set. Then we evaluate the balancedness of the feature spaces learned by the different methods. Here, the balancedness is evaluated by the linear classification model accuracy derivation over all the classes. If the feature space is very balanced, then the balancedness score will be very large. All the classes will have the similar classification accuracy. If the feature space is highly imbalanced, then the accuracy will be quite different from each other or other classes. Then we compare the cross-entropy based supervised learning method and the contrastive learning based self-supervised learning method. We compare their performance on the data sets with different long-tailedness. We can observe that from LT0 to LT, the data set is becoming more and more long-tail, and the classification performance from the supervised learning method is decreasing, while the classification accuracy from the self-supervised learning method is quite stable. And we do another empirical study to study the balancedness of the feature space provided by different methods. How we see that the self-supervised linear method can provide a more balanced feature space because the classification accuracy is quite stable across all the classes, even though data set is quite long tail. But what is the benefit of learning such balanced feature space? Then we do another two sets of the studies to study the generalization performance. We can observe that if the feature space is quite balanced, then it can generalize well to the out of distribution, and also generalize well to other downstream tasks or other domain. And the last figure is showing that if we are using the supervised linear method to learn the representation, and the feature space, the dataset is becoming more and more long-tailed, then the resulted feature space will become more and more imbalanced. Then the accuracy for the auto distribution is actually decreasing. It means that the balancedness of the feature space is actually positively correlated with the generalization accuracy. We can make a similar observation for the downstream task generalization performance. Overall speaking, if the feature space is more balanced, then the generalization performance will be better. So based on such observations, we came up with another new representation learning method that is called K-positive contrastive loss. It is very similar to the contrastive loss, but we are utilizing some class label information to build the positive and the negative classifier sample pairs to compute the contrastive loss. Here, for the positive pair, instead of random sampling from the training data set, instead of using the random data augmentation to generate the positive sample, we are sampling the samples from the same category based on the semantic label information to construct the positive pairs. While for the negative pairs construction, we are sampling the instances from the classes with a different label because we have the access to the semantic label annotation. Here, the number of positive pair where construction is determined by the number of value of the hyperparameter k. Here, k is the number of positive pairs we are going to sample to construct to compute the contrastive learning loss. And for the performance of the KCL, we compare with the classifier retraining. That is the SOTA I just introduced from the decoupling leakages. We can see that the KCL can very significantly improve the performance for the long tail classification compared with the classifier retraining. Very interestingly is that it can not only improve the performance for the medium short and the few short classes performance, but can also improve the accuracy for the many short classes. And overall class accuracy can be also boosted with a large margin. This result can also be observed on the iNaturalist, another data set. So we look into the balancedness of the representation learned from the KCL, and we see that the KCL is actually providing a much more balanced feature spaces than the supervised learning method. Its balancedness is very near to the self-supervised learning method MOCO. And the overall accuracy is much better than the self-supervised learning method and the supervised learning method. So it is actually providing us a feature space very close to the ideal case. The feature space are very balanced, even though the training set is highly skewed, but also the feature space is very discriminative. It can discriminate the classes, the samples from different classes clearly. And to validate our hypothesis, that is the balanced feature space can generalize better, we re-evaluate the KCL for the OD generalization. We train the representation based on 500 classes and evaluate its performance on recognizing another 500 classes. It performs much better than the supervised learning methods, as well as much better than the self-supervised learning method. For the downstream task generalization, we are also very happy to see that KCL is also provide much better performance than the supervised learning method and the MOCO. Okay, so to conclude, in the deep learning area, the common belief is we should do the end-to-end training in every cases for every problem, but maybe this is not always the case for some problems. Because it depends on the laboratory setting. If we have the artificially balanced data set, we can do such end-to-end training. But in realistic, the data set is heavily skewed. It is actually have the long-tailed distribution. So in such case, our work is suggesting that we should inspect the effect from different factors, including the representation and the classifier qualities by decoupling the representation learning and classifier learning. They together determine the final recognition performance. So in the past 2 years, one is published in the iClear. Both of the tools are published in the iClear, and they are convening such message for the long tail classification. The representation and classifier training can be treated separately and can be optimized individually. And a decoupling framework is very helpful for solving the long tail classification problem. And for classification, we can develop some simple yet effective solutions to calibrate the classification model to approximate the testing distribution. This is very important for generalization or for the good performance in the testing case. And for the representation learning, we are revealing a balanced feature space. This is very important for generalization, especially for the long-tailed classification problem. But we are also hoping that the balanced feature space is also very important for other deep learning or other learning applications, such as the OOD generalization, the downstream task solving. So we present a simple approach, KCL, to pursue the balanced feature space, but we are also happy to see the future studies on the balanced feature space, how we can learn a better balanced feature space, and how we can utilize the balanced feature space for other tasks. Okay, thanks again for inviting us to present this work, and that's all for my presentation. Thanks.
Okay, great. Thanks, Jiashi and Bingyi, for the great talk.